Hello, welcome to the course Transducers for Instrumentation. In the last lecture, we discussed some optical sensors which are based on the interferometric properties of uh, optical waves. Means the light which was traveling inside the fiber that had some sort of interference with the returned light or with some measurement which is affecting these optical waves. Today we will discuss about some distributed sensors. Distributed sensors, they are also optical sensors, but they differ in the way they work. For example, we have a very large structure and we want to measure temperature or the strain across all the length. For example, we have a kilometer long dam and we are interested in the the physical strength of this dam because the amount of water it is holding is too much. So we need to be concerned about the strength, how much strength this dam has, and there is no kind of degradation in the structure. So we are interested in the entire length, not at a particular point. So it's a 1 kilometer length, 1 kilometer long dam. We don't want to kind of put 1,000 sensors every 1 meter apart, and even though we do that, there is a possibility that the crack can appear in between that 1 meter. So it's very difficult to do point measurement for large structures, and that is why we use some sort of distributed sensors which are very easy to make using optical fibers. So today we are going to discuss distributed sensors. Distributed fiber optic sensors. And as we discussed, these distributed sensors this offers the ability to measure temperature, or strain at thousands of points along a single fiber. And these are very beneficial for monitoring of large structures. Such as dams, tunnels, pipelines, etc. So all these structures are very much large in the length, and this sensing systems, these sensing systems are based on Brillouin Raman scattering. So these distributed fiber optic sensing, this offers the ability to measure continuously across the entire length. We can measure the temperature or the strain for a very large length, such as dams, tunnels, and pipelines, etc. The property we use in these distributed kind of optical sensor is we shine a very high intensity light into the optical fiber, and this optical fiber is very long in length, perhaps kilometers or even long. We shine a very high intensity of light into this optical fiber, and there is a reflection at every point into the optical fiber. Because this light is very intense, there is a certain amount of light which reflects back across across the entire length of the optical fiber. And this reflected wave, by by the total on by the total time from where we send the light and we receive the light, we can estimate at what point this light is being reflected. Depending upon this time duration, we can estimate at what point this particular wave is reflecting back, and this is how we do the measurement. So the property is we shine a very high intensity light into the fiber, and there is a reflection at across all the length of optical fiber. So the property is, if an intense light at a known wavelength is shown into a fiber, a very small amount of it is scattered back from every location along the optical fiber itself. So when we are shining a intense light into the optical fiber across its entire length, there is a scattering of light, and that light comes back to us, which we can measure using optical detector. Now this optical wave or the light is made up of photons, which has a particular wavelength, what we have already written here. The known wavelength we send with a very high intensity. So the wavelength we know, wavelength means the frequency or the energy of photons we know upfront, what photon we are sending in. When these photons are reflected back from the optical fiber, then if the optical fiber at that particular point, let's say in the middle of optical fiber, there is a zone where the temperature is high, it means we have more thermal energy there concentrated in towards the center of this optical fiber. When this photon is reflected back from that point, this photon receives energy from this temperature, which is higher temperature, or the thermal energy is higher. So this thermal energy gives rise in the energy of photon when it is reflecting back. So what we receive, the reflected wave, is higher in the energy or higher in the frequency, means the wavelength goes down. So we are sending a known wavelength photon into the fiber, and we are getting a photon which is higher in the energy. It means this photon has received some energy somewhere in the optical fiber. So depending upon the difference of energy, we can find out how much is the temperature at that point into the optical fiber, and that point we can calculate based on how much is the round delay of this photon when we are sending and when we are receiving. So there is a phase difference between input and what we receive as the output. So there is a phase difference, so that tells us how far that point is, and the difference in energy gives us how much is the temperature rise. So this is how we do the measurement. So this is the property we use, and based on these properties, when this photon receives energy from temperature, we have two cases. So this, the Raman interaction, this is called Raman interaction. So there are two possible outcomes. The first is the Stoke, we call it Stoke. This is the outcome when the material absorbs energy, the material or the optical fiber absorbs energy and emitted photon has a lower energy. And the second point is anti-Stoke. The second outcome is anti-Stoke, where the material loses energy and the photon we receives has a higher energy than what we send. So these are the two cases when we send a known wavelength of light into the optical fiber. The returned photon may have higher energy than what we send. It means it has received energy from thermal energy in between. And the other case is the received photon has less energy. It means it has lost some energy somewhere in the middle of optical fiber, means some zone has the temperature which is lesser than the normal temperature. It means the thermal energy is lost there to that low temperature. So these are the two cases we have Stokes and anti-Stokes when we shine this intense light. Now these, the structure of this distributed optical fiber is very simple. We have a very long optical fiber. For example, this is distributed optical fiber sensor. we have a very long optical fiber. It may have turn in between, and these distances are very long, typically let's say 120-meter loop. This is 20-meter loop, and let's say this is 100-meter loop. So this is the optical fiber which we are using. Now we shine a high intensity light. So we use some sort of a lens here to couple all the light into this optical fiber. So this is the light, let's say, which comes from here, and this is directed into this optical fiber using this lens. This light is actually sent by laser or something which is very high intensity in nature. So we have another lens which is coupling this light to this laser. We have a laser source. So laser gives you very high intensity of light which goes into this lens, and this intense light is coupled to this optical fiber which is very long in length. So as we discussed, from each and every point of this optical fiber, the photons will be reflected back from this entire length, which is very much big, let's say kilometers. From every point, these photons are reflecting back, and now we need to read these electrons, read these photons. Means we want to measure how much is the energy of these photons. So we can intercept this path in between, where this lens is sending this high intensity light, but as well as receiving these small amount of photons which are reflected back. We intercept this path in between. We are using some sort of a beam splitter here. Let's say this is beam splitter put at 45 degree. So this reflected light will be moved towards this, let's say here, and we have some sort of a grating at this point, and this light again goes to a lens, which couples it to some APD or avalanche photodiode. This is the detector which we will discuss next. This light is coupled to some sort of APD. This is avalanche photodiode, which in fact generates an electrical signal. This is generally, this electrical signal is generally fed to an amplifier, which is all electrical amplifier. So from this onward, all the signals are electrical in nature. So we have amplifier, and then we have certain processing unit, and then we have display. So this is the typical structure of distributed fiber optic sensor. We are shining a light into the optical fiber using a laser which is very high intensity light source. This light is coupled to this optical fiber using lens. So when this light goes in, this is reflected back across the entire length of optical fiber. So photons are coming back as well. So we put in between this beam splitter, which is so this beam splitter is splitting this incoming and outgoing optical wave and sending these received photons towards the avalanche photodiode or APD. This APD is a semiconductor device which detects the photon coming in and generates the equivalent electrical output. This electrical output is generally very small in magnitude, so we prefer to have a amplifier before processing this signal. So this is an electrical amplifier we put after avalanche photodiode. This amplifier amplifies the signal. Then we can use some microcontrollers or our computers to process this data, this amplified signal, and we can put it on the display. So this is how we measure how much is the photon energy compared to what we sent using the lasers. So typical Stoke and anti-Stoke wavelengths are, let's say, anti-Stoke wavelength is typically 1450 nanometer. Again, it depends on what you are sending through this laser, and typical Stoke signal is 1650 nanometer. Based on these frequencies, we classify the Raman filter which we use in this distributed optical sensors. So next we discuss the Bragg grating based sensor, which is a different phenomena of measuring a measurand using the optical properties of material. Bragg grating based sensor is, we put a grating in the optical fiber, and depending upon the grating what we inscribe on these optical fiber, this optical fiber absorbs or reflect certain wavelengths of optical light, and depending upon what is the grating size and grating distance, that wavelength is different. Based on this spacing of these Bragg's grating, we can detect what wavelength is going to come back or going to be transmitted, and this spacing between the grating is the function of temperature. So this is how you can make a temperature sensor using Bragg's grating based optical sensors. So we have Bragg's grating based fiber optic sensor. So this fiber optic fiber Bragg grating or in short we sometimes call it FBG is a type of distributed sensor In this FBG sensor, a short segment of optical fiber reflects or refract particular wavelengths. So we have construction of this FBG sensor something like this. We have a core, and outside we have a cladding. This is our optical fiber, and in the core we put certain grating. Grating means we somehow change the material here. So we change the material across this optical fiber, and let's say we have N1 is the refractive index of core and N2 is the refractive index of cladding, and this grating material, let's say this is N naught or eta naught. So this is the refractive index of material what we use for making this grating, and the distance between these grating is lambda. We have here core and this is cladding. So we have modified our optical fiber itself with a grating, where this grating is nothing but the different material in the core, and where because we use different material, it means the refractive index of this material is different than rest of the core. So core, let's say, have eta 1 is the refractive index, this grating material is eta naught, and the cladding of course is a different N2. If we plot the refractive index graph of this optical fiber, it looks something like we have on the x-axis this is the distance across along this optical fiber, and here we have the refractive index, and we are plotting the refractive index of core. So across this length core is constant at N1, but when the grating is there this changes to eta naught. So this value is eta naught and this is eta 1. So we can see that refractive index of the core changes when there is a grating present, and the distance between the grating is lambda, which is known to us because when we inscribe these grating on the optical fiber, we precisely know what is the distance between these two gratings. So we have this lambda value known to us, and N naught and N1, which is the refractive index of these material, which is also known to us. Then based on the spacing of between these gratings, this grating start reflecting the incoming wavelengths. At a particular wavelength which is very close to this distance, the lambda, the that particular wavelength will be affected by this grating, and rest of the wavelength will be just passed by using this grating. So in the let's plot the input and output waveforms of this FBG sensor. So we send a signal into this optical fiber. So instead of sending a one frequency, we send a band of frequency to this optical fiber. On the x-axis we have frequencies, and on the y-axis we have power. So this is nothing but the wavelength of on the x-axis we have the wavelengths what we send into this optical fiber. So we send a band of wavelength right from the very low to the very high. So and on the y-axis we have the power which we send. So this we can call it a spectral response. So this is our input. When we send these wavelengths into this optical fiber which has grating inside, particular wavelengths will be reflected back to the source itself. So we have in the receiving end we receive all the wavelengths except the one which is reflected back by this grating. So this is the transmitted spectrum. On the y-axis we have power. So we are sending known wavelengths from very low value to very high value into this optical fiber, and because the grating has a particular distance, means this distance when this interacts with the wavelength coming in, particular wavelength will be reflected back by this grating. Rest of the wavelengths this grating will not interfere, and all those wavelengths will be passing by. So at the transmitted end what we receive all the wavelengths except the one which is reflected back by the grating. So we can see here in this graph we are missing this particular wavelength here. This is, let's say, lambda dash, and on the receiving end where on the input side where we are sending this wavelengths, we get this reflected wavelength. This is power and this is the reflected one, reflected wavelengths, and there we don't receive other wavelengths, only this lambda dash. So this is the reflected wavelength which we receive at the input side. And these gratings, these are very simple to make on the optical fiber. We photo inscribed these gratings on the optical fiber during the manufacturing process itself. We can precisely inscribe these gratings and we know the distance very precisely into these gratings. So these gratings are simple elements are simple sensing elements which can be photo inscribed into a silicon fiber. So this is the property which we call fiber Bragg grating based sensor. This is the property we want to use now to make a actual sensor. So what we know is we put a grating, and based on the spacing of this grating, a certain wavelength is reflected back from this grating. So, and this wavelength is a is corresponding to how much spacing we have in between this grating. So now using this property, now we want to make a sensor. So we are making here a Bragg grating based sensor. So this particular wavelength is reflected by this grating, which has a constant spacing in between. Now this spacing we can subject to the measurand. So for example, we want to measure the temperature. So when we expose this grating to the outside temperature, let's say that temperature is higher, there will be a thermal expansion in the optical fiber. Based on that, if there is a thermal expansion, the spacing between these grating changes. So earlier, let's say this is 100 nanometer. When the grating is subject to some temperature which is higher, then this 100 nanometer becomes 110 nanometer. So this difference between the earlier spacing and the new spacing, the wavelength which is reflected back, that wavelength also changes. Earlier, let's say we are getting 600 nanometer wavelength reflected. Now that wavelength will be 650 nanometer. So that reflected wavelength also changes based on the spacing, the difference in the spacing of these gratings, which is proportional to the outside temperature. So this is the property we want to use to make a temperature sensor using Bragg grating based optical sensors. So the construction is again very simple. In this FBG sensor, instead of using a laser, we generally use a broadband source. We use broadband source because we need to send a wide spectrum into the optical fiber. So this is the optical fiber, and here we have, let's say, 3 dB coupler. So what 3 dB coupler does, it splits the waveform. This is the optical fiber here where we have this grating, and we apply the measurand here. This is the measurement zone. This measurand can be anything. It can be temperature, it can be pressure or force, which changes the spacing between this grating. This is the grating. Now this grating will reflect some of the wave which is going primarily going this way, but some wavelength will be reflected back by this grating. That wave will reach here at 3 dB coupler, and this 3 dB coupler will change its path to our detection system. This is a optical detector. This can measure which wavelength is reflected back by this sensor. And now if we plot the input and output, so we send a input where we have all the wavelengths, and at the receiving end, at the optical detector, we receive the input to optical detector. Let's say before application of temperature, the wavelength reflected is lambda dash, and when we apply the temperature, then there is a change in the grating spacing. Because of that, this wavelength will shift, and the new wavelength is, let's say, lambda double dash. So there is a difference between the reflected wavelength, and this difference in the wavelength is dependent on the temperature what we apply in the measurement zone. This is the received signal by optical photo detector. This is the input, and if we measure the optical wave at the far end, it will look something like this. We have this lambda, and this is power, and at the far end we will receive all the wavelength except this lambda double dash. This particular wavelength is lambda dash, and this is lambda double dash. So this is how the Bragg's grating based sensor works. This grating is very particular to a wavelength depending upon its spacing, and if the measurand can change the spacing of this grating, then the wavelength reflected by this grating is different, which is proportional to the measurand. So measurand can be temperature, which can thermally expand the optical fiber, or it can be force, where we are applying a force which can pull this fiber optic sensor, and there is a change in the distance between the grating. It can be pressure, it can be multiple other measurements which we can used to make sensing using of these fiber grating based sensors. Now if we plot the relation between the reflected wavelength and the actual temperature. So this is the temperature, and on y axis we have the wavelength shift. This put this Bragg's grating based sensor gives quite a linear response with the temperature, and we can see the wavelength reflected is increasing because when the temperature is increasing, that is because when the temperature is rising, there is a expansion, thermal expansion is in fiber, the spacing is increasing. It means the grating is now sensitive to the wavelength which are more in length. So that's why we see for the higher temperature the wavelength reflected is higher compared to the lower temperature. So this is the typical output of a Bragg grating based thermal sensor. So this is all about the optical fiber, where we discussed interferometric based sensors, distributed sensors, and Bragg grating based sensor. Now let's discuss about the source, the optical source, which is an integral part of these optical sensors, and the detectors, which is also again as important as the optical source. So before jumping into the optical sources or optical detectors, let's review quickly about some semiconductor physics which is involved in working of these optical devices. So let's brush up some of the device physics. So we know that there are three types of material we have. One is the insulator, and if we plot the band gap of these insulators, we have certain conduction band and we have certain valence band. This is conduction band, and this is valence band. And the energy difference between this conduction band and the valence band, which we denote by Eg or the band gap, this is high. This is typically 6 electron volt or even higher. So if we see the band gap of an insulator, we have conduction band and valence band, and the energy difference between these two bands are very much higher, typically 6 electron volt or even higher. So it's not possible for an electron to jump from valence band to the conduction band. And if there is no free charge carrier in the conduction band, it means the conduction will not happen. If we apply an electric field across this material, then there is no mobile charge carriers in the conduction band which can conduct. So even if we apply a high electric field, there is no current flowing into the material, and this material is called insulator. The second case is we have metal, In metal, we have this conduction band and valence band. They are typically overlapped. This is conduction band and this is valence band, and we have some area which is overlapped. This is valence band. So in metal, we have these, both of these bands are overlapped to each other. It means there is no energy difference between valence band and conduction band, and the electrons in the valence band can go to the conduction band, and they are freely available to move if we apply a electric field. So for a metal, if we apply a electric field or the potential, electric potential, then these charge carriers, which are electrons, they are free to move and they conduct current. So when we apply a voltage across a metal, it conducts current. So these are two typical cases where insulator, the band gap is very high, electron cannot jump at all. In metal, we have no energy band gap. It means the electrons are always available, no matter what voltage we apply, the electrons are available for conduction. The third case, which is a special case, is semiconductor. Semi means half, something like that. So it's a semiconductor. It means it can conduct or it cannot conduct depending upon external influences. So we have here conduction band and valence band, which are not overlapped. So this is a conduction band and this is valence band, and the energy gap is there, which we call band gap, and this band gap now is the order of 1 electron volt. Typically the band gap between the conduction band and the valence band, the band gap is typically 1 electron volt for semiconductors. Now there is a band gap. It means electrons prefer to be in the valence band. They are all available in the valence band, but if they acquire some amount of energy from outside, it may be thermal energy, it may be the energy they acquire from high electric field, the energy which is typically in the order of 1 electron volt. If a electron achieves this much of energy, it can jump from valence to conduction band, and when the electron goes into conduction band, this is now available for electrical conduction. If we apply a electric potential across semiconductor, then this electron can move and it can provide the current. However, if the electron does not receive enough energy, more of the order of 1 electron volt, all these electrons are in the valence band. It means the semiconductor, whatever voltage we apply, it cannot conduct. So depending upon the external factors, this material can conduct, it can become a metal or like a metal, or it can become an insulator, close to insulator. It can conduct the current or it cannot conduct the current based on the external factors. So this is called semiconductor, and typically the band gap of this semiconductor is typically 1 electron volt. So these semiconductors are of great interest, and we make all these optical detectors and optical sources using these semiconductors, and even all the electronic devices we use semiconductor material. A uh, very known, very common material which is semiconductor is silicon we use. So silicon is a semiconductor material very heavily used in electronic circuits. However, for optical devices, we don't use silicon, we use some other materials. We'll come to that point. So here we have semiconductor, where the conduction and valence bands are separated by certain band gap. If we talk about these semiconductor only, at T equal to 0, means the temperature is 0 Kelvin, so there is no thermal energy. So there is no thermal energy available to electrons from outside. So if we plot the conduction and valence band, the conduction band is typically like this, and the valence band is typically like this. At T equal to 0, all the electrons are in the valence band, and conduction band is completely empty. It has available state which electron can fill up, but currently all these states are empty. So I am drawing it by open symbol. It means that these states are available to occupy, but they are empty at T equal to 0. When we increase the temperature, let's say at T greater than 0, means now we have thermal energy. Some of these electrons which are very on the top of this valence band, they have high probability that they will receive this energy from thermal energy, and this electron will jump from maxima of valence band to the minima of conduction band, because this is the least amount of energy they need to jump, and this electron will jump from here to here. This electron can also jump. So some of these electrons which are already high in the energy, they can jump from valence band to the conduction band. So this is EB and this is EC, energy of conduction band. Some of these electrons will jump to conduction band at T greater than 0 Kelvin, when the thermal energy is available to all these electrons. When we have these electrons in the conduction band, now if we apply a external electric field, let's say this is the case when now we have these electrons available in conduction band, these electrons are here and rest of the electrons are still in valence band. Now if we apply a electric field, this is with external bias, at T greater than 0 Kelvin. So when we apply the electric field, these electrons will see a potential difference or electric field in, let's say, x direction, and they will shift or they will move in a particular direction. For example, these electrons will see a drift because of this. electric field. So this shape is not symmetrical now. Some of the electrons will be towards the left because of the external bias what we apply. And based on the electrons are there in the conduction band, based upon the curvature of these bands, these conduction band, the electron mass is different, which is called the effective mass of electron. And this effective mass of charged particle depends on the curvature of this conduction and valence band. So the relation between this, the effective mass and the conduction and the curvature, is 1 over m naught, which is the mass of charged particle, is equal to 1 over h square into d square E by dk square. So this is the relation between the effective mass and the curvature. Curvature is d square E by dk square is the curvature of this conduction or valence band, and m naught is the effective mass of electron. So we discussed today the Bragg grating based sensor and some of the device physics what we need to understand the optical sources and optical sensor. Next lecture we will continue from the device physics and we will see how the optical source actually works. So this is all for today. Thank you.